Okay, in the last class we discussed about Otto cycle as well as diesel cycle, and we also discussed the difference between Otto cycle and diesel cycle. So Otto cycle is constant volume heat addition cycle, and diesel cycle is constant pressure heat addition cycle. In dual cycle or semi-diesel cycle also, it is like combination of Otto cycle and diesel cycle. That means in dual cycle, heat addition is done both at constant volume and at constant pressure. And let us see the PV diagram for dual cycle. So you can see from the PV diagram, process 1, 2 is same. What is the process? Isentropic compression, which obeys the law PV to the power gamma equal to constant. That means reversible adiabatic compression process. The volume decreases from V1 to V2. Then at point 2, the heat addition begins, and first the heat addition is done at constant volume V equal to C. Process 2-3, this process. And then again heat addition is done at during the process 3-4, and during this P equal to C, that means heat addition, but it is done at constant pressure. Process 4-5, which is again isentropic expansion process, and process 5-1 is constant volume heat rejection process. So there will be two heat supplied. So this is QS1 say, and this is QS2, and heat rejection is same. This is QR, heat rejected at constant volume. Okay, so what is dual cycle? The heat addition is done both at constant volume like Otto cycle, but as well as heat addition is also done at constant pressure like diesel cycle. That is why it is called semi-diesel cycle. That is the combination of two cycles, and accordingly the TS, temperature entropy diagram, is 1, 2 is compression isentropic. That is why S1 equal to S2. S means isentropic entropy, and 2 to 3 is V equal to C. That means heat is added at constant volume. Again 3 to 4, so this one is QS1, and 3 to 4 is at constant pressure, and during this time heat is added at constant pressure, and that is equal to QS2. And 4-5, it gives us work output, and during the process 5-1, last process, which is a heat rejection process. Okay, so if we analyze this dual cycle, ultimately we will get a formula like this. Efficiency of dual cycle is 1 minus 1 by R means better to say RC, 1 by RC to the power gamma minus 1, and RC is the compression ratio, and in bracket there will be something alpha into P to the rho to the power gamma minus 1 divided by alpha minus 1 plus this one. Now already we know what is cutoff ratio, V4 by V3. In the PV diagram you can see V4 divided by V3, that is cutoff ratio. At the same time V3 is equal to V2, so we can also write V4 divided by V2, that is cutoff ratio. Now one more ratio comes in this dual cycle, and that ratio is called alpha, that is pressure ratio, which is equal to P3 divided by P2. And what is P3? P3 is the pressure, highest pressure during constant pressure heat addition, and P2 is before heat addition by constant volume. So alpha is equal to P3 divided by 2. So this ratio is for pressure, and the rho is cutoff ratio. That ratio is for volume, ratio of two volumes, and this is ratio of two pressures, higher pressure divided by lower pressure. And in Cutoff ratio, it is higher volume divided by lower volume. Now from PV diagram, you can tell me what are the processes. Okay, just for discussion we are going to tell you will tell me what are the processes. Someone tell what is process. I will write, say process 1 2. What is this process?
Adiabatic expansion.
Adiabatic. So I will write isentropic because the process is isentropic, or adiabatic, you should say reversible adiabatic compression. Okay, good. Then process 2 3.
Sir, constant volume pressure.
Process constant volume. What's say? Heat addition. Yes, constant volume heat addition. Good. And then again process 3 4.
Constant pressure. Heat reduction.
Constant heat addition hobo, again heat addition, because heat addition done in two ways, first at constant volume, then at constant pressure. So constant pressure heat addition, then again process 4 5 is what? Yes?
Sir, isentropic expansion.
Good, very good. Isentropic expansion process. And again process 5 1 is what?
Constant volume heat rejection.
Good, constant volume heat rejection. This is heat rejection. Problem, we will look at the heat rejections and heat addition only. So during the process 2 3, what is QS1, which is equal to Q2 3? We can write Q2 3 equal to how much? Yes, constant volume process.
into minus 2.
Good, T3 minus T, in this case it will be T3 minus T2. This process is 2 3, so higher temperature is T3 and lower temperature is T2. Good. Then constant pressure heat addition, how much? QS2 we can say, and which is equal to Q34 is equal to M.
T4 minus T1.
Now it is MCP T4 minus T3. Excellent. Now again there is another heat, that is we will call heat rejection, and that is equal to during the process 5 1, and that takes place at constant volume, so it will be MCV T5 minus T1. Good. So once we know heat supplied and heat rejected, we can find out net work output as well as the efficiency. So what is efficiency? Net work output divided by heat supply. Now what is heat supplied? In dual cycle, heat supplied is QS1 plus QS2. So both we have to add. So what will be the W net kiman? How much is W net? QS1 plus QS2. That means total heat supplied minus QR. And efficiency how much? Efficiency of dual cycle is equal to W net divided by QS1 plus QS2 both. So if we put the values, then it will be what? MCV T3 minus T2 plus MCP T4 minus T3 minus MCV T5 minus T1, and divided by MCV T3 minus T2 heat supply plus MC.
Sir.
Yes. Qua.
Sir, ये जो MCV T1 minus T5 क्यों ना हो सर? Reduction होगा नहीं?
নহয় তুমি T1 minus T5 যদি লিখো we will get a negative and that negative minus sign we put minus sign. কোনে সুধিছা? That is a good question. কোনে সুধিছা? শিৱম, good. তাৰমানে চোৱা আমি আগতে কৈছিলোঁ heat interaction delta Q is positive if it is heat added, it is negative if it is heat rejected. So this negative thing we already put here. Otherwise you have to write Shivam plus mCV T1 minus T5. গম পাইছা? But T1 minus T5 আমি কি পাম? Negative value পাম না নাই? T1 is smaller, T5 is greater. So আমি আগতীয়াকে কি কৰিছো? Minus into পাতিছো because it is rejected. তাৰপিছত T5 minus T1 to আমি positive value পাম. Both way you can do. You can do it like this. Plus mCV T1 minus T5. যদি আমি 5 to আগত আনো তেতিয়া কি হ'ব? Minus common হ'ব mCV T5 minus T1. এতিয়া বুজি পাইছা শিৱম? Clear? Good. But after this we are not going to do any deduction because in this problem you need not study the deduction part. So simply you try to remember this formula. In some cases you may get some problem solving in the examination. That is very rare, but I cannot say you need not study this. You have to know this formula. In case any question is put, you can simply solve. What will be given? You will be given RC. RC means compression ratio. You will be given the value of, directly you will not get value. RC is what? RC is V1 by, in this problem RC is V1 divided by V2. So if V1 and V2 are given, you can find out RC. Similarly, the another ratio is rho. Rho is what? V4 divided by V3, and that is also equal to V4 divided by V2. So this value we have to find out, or sometimes it may be directly given that cutoff ratio is this. Then again alpha value we have to find out from the pressure P3 divided by P2. So if you get this value, you can get the efficiency of dual cycle. Okay? But from academic point of view, you should know all the cycles. Now there is another cycle that is very important. That cycle we will study in details in the 6th semester in the thermal engineering for gas turbine. And this is the cycle, and that is called, so now we will study what? Brayton cycle. Another cycle is Brayton or Joule cycle. So this simply you have to know what is a Brayton cycle or Joule cycle. Otherwise no problem, you have to solve on Brayton or Joule cycle. So from PV diagram you can say the same processes. Process 1, 2 is what process? Someone tell me. From PV diagram.
Isentropic compression.
Good. So process 1, 2 is isentropic compression. Same. It is like Otto cycle or diesel cycle or dual cycle. Same. Now process 2, 3 is what? Constant pressure heat addition cycle. Okay. Heat addition to we will represent like this, QS. Now process 3, 4 is what?
The adiabatic process.
Adiabatic or isentropic expansion. Excellent.
Expansion.
Excellent. Now process 4.1. What is this process?
Sir, constant pressure heat reduction.
Yes, exactly. So you know what is Brayton or Joule cycle. So what is a Brayton or Joule cycle, which is used in gas turbine to produce electricity in the turbine. Generally there are two types of turbine. One is three types of water turbine. You have studied, I think. Water turbine, steam turbine and gas turbine. So in gas turbine the working fluid is gas. That we will study in details in the 6th semester only. But You have to know gas turbine uses Brayton or Joule cycle. So what is the difference? Only difference with other cycle is what? Someone tell from this? I will not tell it you. You can you yourself can tell what is this, what is the difference of Brayton or Joule cycle from other cycles?
Heat is rejected at constant pressure.
Excellent. Heat is rejected at constant pressure. But otherwise, heat addition already you have discussed that heat rejection is done at constant volume in Otto cycle, at constant pressure in in diesel cycle, and both at constant pressure and volume in dual cycle. But in all these three cycles, heat rejection was done at constant volume, but only difference with the Brayton or Joule cycle is that heat rejection is done at constant pressure. Very good. Now the temperature entropy diagram for Joule cycle, another name is Brayton cycle, okay, is like this. Process 1, 2 is constant entropy S1 equal to S2. Process 2, 3 is heat supplied at constant pressure. Process 3, 4 is work of the turbine, because process 3 is expansion, which is for the turbine. The turbine expand the gas and it produce the power. And process 4.1 is heat rejection at constant pressure. That's it. Okay. Now let's see how the heat is interacted. So during process 2, 3 in the PV diagram as well as in the TS diagram, Q2, 3, which we call QS also, heat supplied, is equal to, it is done at constant pressure, so it will be mCp T3 minus T2. Generally in SI unit we express the heat in Joule or kilojoule. That is why I am writing the unit kilojoule, because in the next class or so we are going to solve some problems in which we have to use the units for heat and work, and for both these interactions, heat or work, we will use the SI unit, which is Joule, and most commonly we use the kilojoule. That means 1000 joule equal to 1 kilojoule. So QS we know what is heat supplied. Then again heat rejected during the process 4.1 in PV diagram as well as in TS diagram. At constant pressure, both are at constant pressure. So this we will call heat rejected, and during the process 4.1, that is why Q41 is equal to mCp. Why Cp? It is done at constant pressure. T4 minus T1. What is T4? Temperature before heat rejection minus temperature after heat rejection. That means this is dT, temperature difference, and this is also dT, temperature difference. Okay. So if we know heat supplied and heat rejection, we can find W net. What is W net? W net is what? W net is QS minus QR, and QS is this one and QR is this much. So we can easily cancel all these terms. So what will remain? 1 minus T4 minus T1 divided by T3 minus T2 in terms of temperature. And if we simplify this, then we will get what? In terms of pressure ratio, not in temperature ratio, sorry. So ultimately we will get efficiency is equal to 1 minus 1 by Rp to the power. What is Rp? Gamma minus 1 by gamma. Now what is Rp? Rp is equal to pressure ratio. That is equal to high pressure divided by low pressure, P2 divided by P1 and also P3 divided by P4, because this is constant pressure, P2 is equal to P3 P2 equal to P3 and P1 equal to P4. So RP is pressure ratio. In Otto cycle we got efficiency of Otto cycle was 1 minus 1 by Rc to the power gamma minus 1. Okay, can you remember this one? And efficiency of this cycle, that means Joule cycle, efficiency of Joule cycle. This efficiency is equal to 1 minus 1 by Rp to the power gamma, and there is very little chance that you will get any problem to be solved in the examination for Brayton or Joule cycle. Little, but you should know what is Brayton or Joule cycle. In gas turbine, what is the cycle used, or in Brayton or Joule cycle, what is the difference with Otto cycle, or what is the difference with diesel cycle. That type of comparison you should know, and that is enough for this semester, for this course. In future we will study the thermal engineering. This is the basic, that is thermodynamics. So a quick recap, we have already studied Otto cycle, for which efficiency is equal to 1 minus 1 by Rc to the power gamma minus 1, and diesel cycle efficiency is 1 minus 1 by Rc to the power gamma minus 1 into 1 by gamma into rho to the power gamma minus 1 divided by rho minus 1. And for dual cycle, then what is efficiency for Joule or Brayton cycle? Efficiency is 1 minus 1 by Rp to the power, not gamma minus 1, remember this is gamma minus 1 divided by gamma. Now can you tell me what is the difference between Otto cycle and diesel cycle? At least one difference. From heat addition point of view, you tell the difference. So Otto cycle, diesel cycle, dual cycle, Brayton cycle. So if we try to make some difference comparison, so first heat addition. Heat add at key Otto cycle is done at constant volume. How? V equal to C. Heat addition is done at constant volume. In diesel cycle, it is done at constant pressure. In short, likhisu. And in dual cycle, it is V equal to C and P equal to C. That means heat addition is done at both constant volume and constant pressure. And Brayton cycle, heat addition? Good, very good. Now heat reject, constant volume. Diesel cycle, constant volume. Dual cycle, constant volume. But at Brayton cycle, it is at constant pressure. Because from this, you can get the picture of the cycle. PV diagram picture you can get from this thing. Okay, then you can immediately, instantly, you can draw the PV diagram. If you can remember this, you can look at the picture. You imagine the picture, PV diagram for Otto cycle. V equal to C, that means line is vertical in PV diagram. Diesel cycle, the heat addition line is horizontal. Dual cycle, both vertical and horizontal. So we can say Otto cycle heat addition is like this, diesel cycle heat addition is this, dual cycle heat addition is this, and Brayton cycle heat addition is this. Okay? Good? And heat rejection is vertical line hobo. PV diagram, vertical line, but in this case it is horizontal line in PV diagram. Or the efficiency of Otto cycle is more than diesel cycle if they are of same compression ratio. But diesel cycle is used at higher compression ratio, and therefore we get more efficiency for diesel cycle. But if we adopt the same compression ratio within the range of petrol engine compression ratio, Otto cycle compression ratio, then we will get more compression, more efficiency in diesel Otto cycle. Okay, more efficiency. But we will not compare with Brayton cycle, because Brayton cycle is completely used for other purpose in different type of engine, which we call rotary engine. That we will discuss in the future. Okay. And if we use the same pressure or temperature, same pressure, high pressure and temperature যদি আমি ইউজ করো, then efficiency of diesel is more than efficiency of dual, and efficiency of dual is more than efficiency of Otto. If the compression ratio is same, that means V1 divided by V2, then efficiency of Otto cycle is more than efficiency of diesel cycle. But if we consider the temperature and pressure, particularly pressure, high pressure, low pressure, there will be one maximum pressure, one minimum pressure. So if we consider the pressure point, same pressure jodi range ami use karo, then diesel cycle efficiency is more than dual cycle, and which is more than the Otto cycle.